Today we are going to discuss atomic scattering factor or form factor. Actually this atomic scattering factor, which is also known as atomic form factor, this is a fundamental concept in X-ray crystallography, and its study is very essential for understanding the structure and properties of crystalline materials at the atomic level. In fact, when you talk about atomic scattering factor, how it is defined, how it is calculated, all these things we will learn in this lecture. And I would like to share with you that this is a very important concept, and always you have been asked questions regarding this atomic scattering factor in different examinations. That may be a university examination of BSc or MSc level, or the competitive examinations like civil services examination, in which your optional is physics. So watch the complete video seriously and note down these things in your notebook. And as I always told you, that when you will note down these things in your notebook, that will be a good assignment, a good notes for your examination purpose. Because I always write all the facts in the video. When you watch other videos, you don't find everything written there. But for your convenience, I always write all those things which are needed to write down in your examination, and so that you will have a complete idea even when you read your notebook, then the concept becomes clear. Okay. So what is this atomic scattering factor or form factor? In fact, you have studied the X-ray scattering, and we have studied the two basic tools for X-ray scattering, and those are Bragg's treatment of X-ray scattering or diffraction of X-ray, and the Law treatment. Okay, and both of these treatment deals with the diffraction of X-ray at atomic level. Okay, at point level, not atomic level, but at point level. Actually, this atomic scattering factor deals with X-ray scattering on atomic level. It means we discuss the X-ray scattering by an individual atom in a crystal. Okay, and this scattering will be just a function of a scattering angle, and it also depends on the type of atom and the wavelength of the X-rays. Okay, so now we start to know about this atomic scattering factor in detail. And as I have told you, if you will watch the complete video, the concept regarding this atomic scattering factor, which is a very important concept, or very, you can say, a crucial concept of X-ray crystallography, that will be crystal clear to you. And as I have told you that in my previous lecture, I have discussed in very detail the two treatments of X-ray diffraction. First one was Bragg's treatment, and another was Law treatment. And in both of the treatments, we have studied the conditions for X-ray diffraction. Okay. But you can remember, if you have not watched my previous videos on the X-ray scattering by Bragg's treatment and Law treatment, I will suggest you go through those videos first, and after that you should watch this video, and then the concept will be clear. But a question arises here: what we have learnt in the diffraction of X-ray in Bragg's treatment or Law treatment. and learnt about the conditions which refers that when X-ray diffraction will take place. The conditions of the condition mentioned in Bragg's treatment and Lowe treatment for X-ray diffraction are realistic. A usual question arises: that is possible in practice? The answer is definitely not, because when you talk about the diffraction of X-rays by a crystal, and you use to explain this diffraction of X-ray or radiation by using the Bragg's law or the Love's equations, then you can remember we always talk about the scattering point center. In both of the treatments, we consider that X-rays are incident on a point scattering center and then it gets scattered. But in a real crystal, is it possible that the scattering will take place from a point scattering center? When you talk about a real crystal, you know the crystals are made up of atoms, and these atoms are located at the lattice points. In a crystal, the smallest point mass is electron. But are these electrons located at the lattice point? Answer is no. At the lattice points, atoms are located. And you know, an atom consists of a large number of electrons. So, in practice, the scattering of X-ray will take place by atoms, not by electrons, not by a point scattering center. When you say point scattering center, that means electron. So I have written here, you can see that these diffraction conditions mentioned in Bragg and Lowe treatment are not realistic. These are not realistic situations, because according to these conditions, the diffraction of X-rays take place from point scattering centers around an space lattice. Okay? And since electron is the smallest scattering center, the diffraction conditions would ideally be applicable to a lattice in which every lattice point will be occupied by an electron. But in actual practice, the lattice points are not occupied by atoms, but these are occupied by but in practice the lattice points are not occupied by not atoms, but you have to say electrons. Here at the place of atoms, we should write electrons. Lattice points are not occupied by electrons. Okay? But in practice, lattice points are occupied by, lattice points are occupied by atoms, not by electrons. So atoms, the word atom here was correct. Atoms. Okay? Which contains a large number of electrons. Okay? If you consider that Z be the atomic number of our crystal, then in an atom there will be Z electrons. It is a basic fact. So, what we have learnt? According to the diffraction conditions which we study in Bragg treatment and Lowe treatment, in those treatment it is considered that an X-ray beam is incident on a scattering center which is just a point scattering center, and in case of crystal that will be an electron. So according to those treatments, X-ray will incident on an electron and then it will get scattered. But in practice, at the lattice point there is not the electrons are not located, but we know at the lattice point atoms are located. and an atom consists of a large number of electrons. Okay. So actually the condition on which Bragg's treatment and Lowage equation are based, they are not realistic, but they are ideal situations. In a real situation, the scattering of X-ray will take place from atoms, not by electrons. Okay. Apart from this, there is also a very serious problem of phase. Let us consider that this is your atom. This small sphere represents an atom, let us consider. Okay. And X-ray beams are incident on this. You know, the X-ray beam will be scattered from the different points or different parts of these atoms. Okay. Since the wavelength of the X-ray is of the order of the dimension of an atom, and so when the X-ray will be incident on the atom, it will get diffracted, or they will suffer Bragg's reflection from different points or different portions of the atoms. Okay, as I have shown in this figure, let us see this first beam is scattered from this point, let us say A, and the second beam is scattered from this portion B, and the third beam, let us say, is scattered from this point C. Okay. So these are the different portions or different points located on the atom from where the diffraction of X-ray takes place. Okay. Since the X-rays get diffracted from different portions of an atom, so in general, the scattered beams are not in same phase. So this first beam differs in phase with the second beam and with the third beam and so on. So the scattered beam in general, you can say, are not in same phase. Okay. Now, if you consider that the amplitude of the X-ray scattered by a single electron is equal to psi e. Okay. And in an atom, there are Z electrons. Okay. Z electrons. Then the amplitude of the X-ray scattered from the atom in general is not equal to Z times psi e, where Z is the total number of electrons and psi e is the amplitude of the scattered X-ray beam from an electron. Okay. Then the amplitude of the X-ray scattered from the atom in general is not equal to Z times psi e. Why it is not in general equal to Z times psi e? Because this scattered beam has actually phase differences. If all these beams will be in same phase, then this will happen. Then psi a will be equal to Z into psi e. But as there is a particular phase difference between the scattered beams, and that's why the amplitude of the X-ray scattered from the atom in general is not equal to number of electron times the amplitude of X-ray scattered by a single electron. Okay. So I have mentioned it here. You can see that amplitude of X-ray scattered by a single atom, which I have denoted by the symbol psi a, that is in general not equal to Z times amplitude of X-ray scattered by a single electron. Okay. Symbolically, you can say that psi a is not equal to Z into psi. In fact, it is found that in general, this psi a is less than Z times psi e in general. In a limiting case, it is possible that psi A will be equal to Z into psi E, but in general, it is found that the amplitude of the X-ray scattered by the atom as a whole is less than the product of the number of electrons times the amplitude of X-ray scattered by a single electron. And so you can say that psi A divided by psi E, this will be in general less than Z, where Z is the total number of electrons in the atom. Actually, this ratio of psi A and psi E, this is denoted by the symbol F, and this F is nothing, this is called the atomic scattering factor or the form factor. Okay, so F, which is F will be less than Z. So you can say how this form factor is defined. Actually, this atomic scattering factor or this form factor is defined by the ratio of amplitude of radiation or X-ray scattered from an atom to the amplitude of radiation scattered from an electron. So when you will divide the amplitude of radiation scattered from the atom as a whole by the amplitude of the radiation scattered from a single electron, then the number obtained is denoted by the symbol F, and this ratio is called atomic scattering factor or form factor. And as I have told you, in general F is less than Z, but you will see in the last of this lecture that in a particular case, particular limiting condition, this F approaches to Z. It means you can say that the maximum value of form factor is equal to Z, maximum value. Okay, but in general F is less than Z. F is less than Z. But in a limiting condition, F may approach to the value of Z. Okay. So this is the basic definition of the form factor or the atomic scattering factor, and I hope you have clearly understand how you can define this atomic scattering factor. Okay. Now, after knowing the basic definition or basic meaning of atomic scattering factor, our aim is to find the expression for measuring this atomic scattering factor. So let us make a calculation to get expression for the amplitude for the atomic scattering factor or the atomic form factor. Okay, how we can calculate it, and now let us see. But before that, one thing I have mentioned it here, this is also a very remarkable fact. You can see, in an atom there are 2 point charges, 2 types of point charges. One type of point charges is electron and another is positively charged nuclei. These are nuclei. Here we are considering the diffraction of X-ray from the electron, not by the nuclei. Why? Why the diffraction of X-ray is not considered with the nuclei? The reason is very obvious. Actually, the interaction between the X-ray and the nucleus is very weak. It is not a strong interaction. And due to this weak interaction of X-rays with the nuclei, the scattering due to nuclei is neglected compared with that due to the electrons. It does not mean that that the X-ray will be completely not diffracted by nuclei. There will be some diffraction, but the diffraction of X-ray from the nuclei is negligible in comparison to its diffraction from the electrons. So in our calculation, in our discussion, we neglect the diffraction of X-rays from the nucleus. Okay. Thank you. I hope the basic definition of atomic form factor, why nuclei are not considered for the diffraction of X-ray. These all things are now clear to you. Now our aim is to calculate or to find the expression for the form factor or atomic scattering factor F. This is actually the most important thing of this lecture. Okay, and for this let us see in this figure you can see the sphere which I have shown in this figure. This actually represents an atom. Okay, and for convenience here we are considering that the electrons of the atoms are distributed uniformly in this spherical volume, and the radius of this sphere I have taken R, and its center is at O, which is taken as origin for the measurement of distances. Okay, and mark, I am considering that the charge distribution of electron in the volume of the atom is uniform charge distribution we consider. Okay, and we also consider that there is an electron situated at the center of the atom, which you can see it here. There is an electron here, and we also consider a small volume element dV. You can see it here at this point, let us say P, and this volume element actually makes a very small angle, let us say d phi, at the origin. Okay, at the origin. Now we will consider the scattering of X-ray incident on the single electron located at the origin and the X-ray scattered from this volume element. But before that, let us consider that this rho of R, this is volume charge density. This is volume charge density. Okay, and if rho of R is the volume charge density at this point P, whose position vector is R with respect to the origin, then can you say what will be the charge content in this volume element? You know, since rho is the volume charge density, it means in unit volume the charge is equal to rho. Okay, so in volume dV the charge will be rho dV. So this volume element actually contains a charge dq which is equal to rho dV, and this also acts like an scattering center. Okay, now let us consider an X-ray beam is incident on the electron situated at the origin O, and we have considered this kappa naught. You can see this kappa naught, I have considered a unit vector in the direction of the incident beam. The another beam is also incident on this volume element dV, or you can say the charge element rho dV, and this incidence direction is also represented by the unit vector kappa naught. And these beams get scattered, and kappa hat, I have considered the unit vector in the direction of the scattered beam of X-ray. So you can say that kappa naught represents the direction of incidence, and kappa denotes the direction of scattering. Okay, this denotes the direction of scattering. Now, for calculation, I have considered that this line, let us see, I am writing it xy. This is not a line, since I have shown this in a two-dimensional plane. So this appears like a line, but this is actually the plane, or you can say scattering plane. Okay, and with this scattering plane, or you can say this is Bragg's plane. This scattering plane is Bragg's plane. And the incident beam you can see makes an angle theta with this Bragg's reflecting plane. So this theta is nothing, this is the glancing angle, okay? And this theta is also also glancing angle, okay? Now, when the X-rays are get scattered, then I have taken a vector n which is called a scattering normal vector, and definitely you have an idea of this scattering normal vector because you have studied this scattering normal vector when we have studied the Lowes equation. Remember that, okay? And this n is nothing, this will be simply the difference of kappa and kappa naught. All these things I have mentioned it here, you can see. Consider an atom containing electrons arranged in a spherically symmetric configuration around its center at O, which is taken as origin. Consider a volume element dV at R, okay? And this rho of R, this is volume charge density at R. Rho R dV, this is charge of the volume element. Kappa naught, a unit vector in the incident direction. Kappa, a unit vector in the scattered direction. And you can see this is your scattering plane, or you can say the reflecting plane, and this line represents the incidence direction, okay? Incident direction. And here this line represents the scattered direction, okay? And this line, let us say this line is PQ, is normal to this scattering plane, and a vector represented by this PQ, which I have written N, this is called the scattering normal vector. And it is obvious from triangle law of vector addition that this N will be equal to what? This will be kappa minus kappa naught. But kappa and kappa naught both are the unit vector, and you know modulus of A minus B, mod of A minus B is simply equal to 2A sine theta by 2. But when? If mod of A is equal to mod of B. Do you know this formula? This is just a subtraction of two vectors of equal magnitude. When the magnitude of two vectors A and B are equal and theta is the angle between vector A and B, then the mod of A minus B is equal to 2A sine theta by 2. Okay? Here, if you want to find the modulus of vector n, that means mod of kappa minus kappa naught. But kappa and kappa naught both are the unit vectors. So, using this formula 2a sine theta by 2, what will be the modulus of n? This will be 2 into 1. 1 is what? This is mod of kappa equal to mod of kappa naught, and that equal to 1. Okay? And sine 2 theta by 2. See the figure. This is your vector kappa and this is your vector kappa naught. The angle between these two vectors is 2 theta, not theta. Okay? So this will be sine 2 theta by 2. And this 2 and 2 will cancel out. And so this is simply 2 sine theta. So modulus of this scattering normal vector is 2 sine theta. We will need the value of the modulus of a scattering normal vector in our calculation sometimes later. You will see later on. Okay? Now, as you can see, the X-ray beam is scattered from this volume element and that is scattered from this single electron. In both a scattered beam will have actually a path difference. Okay? And corresponding to that path difference, there will be a phase difference. For getting the path difference between them, you have to draw actually a normal from the scattering from this point on this and on this, and then you have to add those. But how we can find that path difference? You have already learned while studying the Lagrange equation. So you can remember that, or you can watch my video on Lagrange equation, and you will see that the path difference between the waves scattered from the charge element rho r dv and that from the electron situated at O, if that phase difference is equal to phi r, what will be that? You know, phase difference is equal to 2 pi over lambda into path difference. Here lambda is the wavelength of the scattered radiation. Okay? And as it is evident from the geometry of figure, and you have also learnt about this in my lecture on Lagrange equation, that this path difference is equal to r dot n. Okay, and you can see this is your vector r, I have shown in that figure, and this is your vector n, and the angle between these two vectors is phi. Okay, this is phi. You can see the figure. This angle is phi. Actually, this vector is r, and this vector will be also r, because this element is very small. Okay, and so angle between this r vector and n vector is equal to phi. Okay, so phi r, which is phase difference between the scattered radiation from the volume charge from this charge element and the single electron situated at the center or at the origin, that will be equal to 2 pi over lambda times r dot n. Okay. Now, the scattered radiation can be represented just like a plane wave. A scattered radiation, we can take it like a plane wave. So if you consider that k is the wave number or the magnitude of wave vector, omega is the frequency of the scattered radiation, and it covers a distance x in the direction of the in the direction of the scattered direction, then the amplitude of the wave scattered from the single electron at O can be given as psi e equal to a e to the power I kx minus omega t. So this equation represents the amplitude of the X-ray scattered from the electrons situated at the origin O. Okay. And as I have told you that this x is the distance covered in the direction of this scattered unit direction, and k is the wave number, or you can say k is actually the magnitude of the wave vector. Okay. Now we have to find the amplitude of the scattered wave from the charge element rho r dv. Actually, when you talk about the amplitude of the wave scattered from this element, definitely in its expression you have to introduce this phase difference, because the wave scattered from this element differs in phase with the wave scattered from the electron. Okay, scattered from the electron, and so we have to introduce that phase difference. And again, you should think that actually the amplitude of the wave scattered from this volume charge element is also proportional to the charge of the element. So the amplitude of the scattered wave from the charge rho r dv is given like this: d psi a equal to a e to the power I kx minus omega t plus phi r. You can see the phase of the wave scattered from the electron at time t is kx minus omega t. but the phase of the wave scattered from this volume element, that will actually differ by phi r in phase. So I have added this phi r in the phase term. Okay, and so you can say that the phase of this scattered radiation from the volume charge element differs in phase by phi r from the phase of the wave scattered from the electron. And since this must be also proportional to the amount of charge contained in the scatterer, and so I have multiplied it by rho r dV. Rho r dV. Actually here I use the vector sign here, but since the charge distribution is spherically symmetric and uniform, so you can guess that this volume charge density will depend only on position, not on direction. So instead of vector r, you may also write only r. It means the charge density will be only a function of r, not its direction. But that we will use sometime later. Okay. Now we have defined two amplitudes. First of all, you have defined the amplitude of the wave scattered from the electron at O. Then you have defined the amplitude of the wave scattered from the volume element, and I have denoted this amplitude by psi e and this d psi a. Okay. So the ratio of the amplitude of the radiation scattered from this volume element, that is d psi a, and that from the electron will be what? Actually this ratio is denoted by the symbol df. So df will be d psi a divided by psi e. But you have seen that d psi a is equal to this much. This is a e to the power I kx minus omega t plus phi r. But I have written it as this multiplication. You can write this factor e to the power I kx minus omega t plus phi r as e to the power I kx minus omega t times e to the power I phi r. Okay. And the remaining factor is rho of r dV. And psi e, this is this much. Okay. Now you can see this factor will cancel out. And so df is equal to e to the power I phi r times rho of r dV. This is the ratio of the amplitude of the wave scattered from a volume element of the atom, and that due to an electron. But according to the definition of the atomic scattering factor, we have to find the ratio of the amplitude of wave scattered from the atom as a whole and that of the electron. So getting that, you must integrate this equation 4. So when we will integrate this equation 4 for appropriate limits, then you will get actually the ratio of the amplitude from the whole atom to that from the electron. And that ratio is called atomic scattering factor, which we have denoted by the symbol F. So you can say F is equal to integral over V, where V is actually the volume of the entire atom, a rho of r e to the power I phi r dV. Okay. So this is the expression for the atomic scattering factor. But now we have to evaluate this integral. And how we can evaluate this integral? Since the charge distribution is spherically symmetric here, so this problem can be handled more conveniently when you will use the spherical polar coordinate system. So let us use the spherical polar coordinate system to make our further calculation. And in a spherical polar coordinate system, what will be this volume dV, okay? and how we will find the phi r, everything now let us see. As you have seen earlier that this phi r, which is the phase difference between the waves scattered from the volume element and that from the single electron, that was given by 2 pi over lambda times r dot n. But since you have seen that angle between vectors r and n is phi, you have seen earlier. So according to the definition of a scalar product, you can write this, that this is 2 pi by lambda Rn cos phi, Rn cos phi. But you have seen that this n, which is magnitude of the scattering normal vector, you have seen that this is equal to 2 sine theta. Okay. So instead of this n, I have written here 2 sine theta. Okay. And so you can say that this phi r is equal to 4 pi over lambda times r times sine theta cos phi. And this can be written for convenience, phi r equal to mu r cos phi. Phi r equal to mu r cos phi, where I have written this mu for 4 pi by lambda sine theta. Okay. So in this way we have defined phi r. Now as I have told you that we will define this the value of this volume element dV in a spherical polar coordinates. And in spherical polar coordinate, a volume element is just defined as a thick shell, whose periphery, or you can say length, is equal to 2 pi r sine phi. This is the length, and its breadth is r times d theta, and its height or width, you can say, is equal to r d phi. So this is length, this is breadth, and this is width. So there is a, you can imagine there is a spherical shell whose thickness is r d theta, width is r d phi, and its length is 2 pi r sine phi. So the product of 2 pi r sine phi times r d theta into r d phi, which is equal to this much, this is 2 pi r square sine phi d phi dr. This is the volume element dV in the spherical polar coordinates. And for a clear-cut idea how we can find this volume element, you can watch my video in the playlist of mathematical physics in curvilinear coordinates, where you will get the expression for the volume element in all coordinate systems, in the spherical polar coordinate system, in cylindrical coordinate system, in Cartesian coordinate system, and in curvilinear coordinate system. You can watch that video. Okay. Now substituting the value of phi r, which is mu r cos phi, and dV equal to this much 2 pi r square sine phi d phi dr, in this equation 5, let us put the appropriate limit to get the value of f. Here the limits for r has been written 0 to infinity. But don't confuse with this infinity. Infinity means the maximum value of r. In practice, whenever you will talk about an atom, the maximum value of r will be equal to the radius of the atom. If you denote that by r, capital R, that will be simply r. So it does not mean that we always put here infinity. Infinity is the symbol which refers the maximum value of this small r. Okay, and at the center, r will be equal to 0, and at the periphery of the atom, this r will be equal to capital R. But for different atoms, this will be different, so I have written here infinity. As in quantum mechanics, when you define the normalization condition, you write for all space minus infinity to plus infinity. That does not mean that we have always put the value minus infinity and plus infinity. That refers the minimum and maximum value. Okay. And, and the value of phi, you can see the figure, phi varies from 0 to pi. This is your phi, and this phi will be from 0 to pi. Okay, from 0 to pi, this much. So the limits for the second variable, that is pi, is 0 to pi, and the integrands are rho r times e to the power I mu r cos phi times 2 pi r sin phi d phi dr. Okay. Actually here we are going to integrate with respect to two variables. One variable is our phi and another is r. So let us separate this integral for the two variables. So you can write f equal to integral for r from r0 to infinity 2 pi r square rho of r dr times integral e to the power I mu r cos phi times sin phi d phi for phi 0 to pi. Okay. Now let us first of all try to evaluate the second integral, that is integral of e to the power I mu r cos phi times sin phi d phi. This integral can be easily evaluated by the method of substitution. And for this, let us consider that cos phi is equal to z. We consider it. And so, taking differential, you will have minus sin phi d phi equal to dz. Okay. Now, for limits, you can see when phi is 0, then what will be this z? Z will be cos phi means cos 0, which is equal to 1. And when phi is pi, then z will be cos pi and cos pi will be minus 1. So instead of these limits 0 and pi, we will put here 1 and minus 1. Okay? And at the place of sin phi d phi, we will place minus dz. So this integral becomes integral from 1 to minus 1 minus e to the power I mu r z dz. Okay. Now, if you will make this minus sign plus, you can interchange the limits. So after interchanging limits, this minus becomes plus. And the integral of this e to the power I mu r z will be what? This will be e to the power I mu r z divided by I mu r. Okay? And limits are minus 1 and plus 1. Okay? Now let us substitute the limit. The limits are for z. And so this will be 1 over I mu r times e to the power I mu r, because z is 1. And minus now e to the power I mu r times minus 1. So I have written here e to the power minus I mu r. Okay. Now let us multiply by factor 2 in the numerator and denominator. So you can write this expression as 2 divided by mu r times e to the power I mu r minus e to the power minus I mu r divided by 2i. But can you say the factor inside this square bracket is what? This is simply sin mu r, because you know sin theta, you know Euler's formula. This is e to the power I theta minus e to the power minus I theta divided by 2i. So using this formula, you can write that this square bracketed factor is equal to sin mu r. And that's why this integral is equal to 2 sin mu r divided by mu r. Okay? So in this way, we have obtained the value of this integral. Although there is no need to calculate this, to make this calculation. You can remember this result and directly put here in this equation 9. And so now let us use this equation 10 in equation 9, and you can write what will be f. Okay. In this condition, you can see f will be equal to integral 0 to infinity 4 pi r square rho of r sin mu r over mu r dr. Okay, and this is actually the general expression for the atomic scattering factor. Okay, atomic scattering factor. Actually, the evaluation of this integral depends on the nature of the atom, on the nature of the charge distribution, and that calculation is made by various approximate methods like Hartree method, Thomson's method. There are so many methods utilized to obtain this result. Now you can see this graph. Actually here, this atomic scattering factor F have been plotted in against of sine theta by lambda. And it is evident this is just an experimental curve. Not I have plotted it on the basis of any formula. It has been found from experiment. For different scattering angle and different wavelength, when you will plot F in against of sine theta by lambda, a curve like this you will obtain. And this is for this experimental curve is for magnesium, whose atomic number is equal to 12. And you can see when theta tends to 0, that is at this origin, theta will be 0. And when theta is 0, you can see the value of F is equal to 12. It means when you can say that when theta tends to 0, then F tends to Z. This is the limiting condition. As I have told in the definition of atomic scattering factor, that in general F is smaller than Z, but in a particular limiting condition, this F may approach Z. So you can see, when the scattering angle theta tends towards 0, then atomic scattering factor tends to the atomic number or the total charge of the electron. You can see. Actually, this is also evident from this equation too. How you can say? See it here. When actually this theta tends to 0, then see what will be this mu. We have written this mu instead of what? 4 pi by lambda sine theta. When theta tends to 0, sine theta will be 0, and if sine theta is 0, mu will be 0. Okay, the page has been turned, but this will be just okay. Let us see. Yes, you can see from here, if theta tends to 0, sine theta will be 0, and that's why you can say that mu will tend to 0. So we can say that when theta tends to 0, then mu also tends to 0. And if mu tends to 0, this sine mu r over mu r, this will tend to 1, because you know limit theta tends to 0, sine theta by theta is equal to 1, and this will be equal to 1. And when it is 1, then what will be F? F will be then simply equal to integral 0 to infinity 4 pi r square rho of r. Okay? All those things I have mentioned it here. You can see the variation of F with sine theta by lambda for mg, whose z is 12, has been plotted and shown in that figure. As you can see, as theta tends to 0, F tends to z. The same result is obtained from A, since for theta tending toward 0, mu will tend to 0, and this sine mu r by mu r will tend to 1, and so F will be equal to this much. Okay? But can you say, what is this 4 pi r square rho r dr? Actually, 4 pi r square dr, this represents the volume of a spherical shell of thickness dr, and when you will multiply it by rho, then this represents the charge content in a spherical shell of radius r and thickness dr. So integrand 4 pi r square rho r dr represents the charge contained in a spherical shell of radius r and thickness dr. Okay? And when you will integrate it for all possible values of r, then what will be your result? Then you will get the total electronic charge stored in the atom. And what is that total charge? The total charge will be equal to Z into E, where E is the charge of an electron. If you consider that charge of electron is unity, then that will be simply equal to Z. So Z represents the total charge, but when we consider that electronic charge is 1. Okay? So I have mentioned it here. The integrand represents the charge inside the spherical shell of radius r and thickness dr, and hence the integral gives the total electronic charge stored inside the atom, that is Z. So as I have told you in the beginning, that in a particular limiting condition, this F may tends towards Z. So you can see when theta tends to 0, when a scattering angle is theta, when a scattering angle tends to 0, it means there is no scattering. In that condition, this atomic scattering factor is just equal to the total electronic charge. But when theta is not 0 or it does not tend towards 0, then F in general is smaller than Z. Okay? So in this way, we can obtain the value of the atomic scattering factor, and what it refers you can learn. So I think the idea of atomic scattering factor is now very clear to you. So just I have suggested you in the earlier in my lecture that you should note down this in your notebook. So definitely watch the video seriously and note down this in your notebook, and definitely that will be very helpful to you. Thank you very much.